So today we will have Nikolay Bobev, who will tell us about the unreasonable effectiveness of higher derivative supergravity in ADS4 holography. And before I let him talk, I would like to thank him very much because he accepted on a very last time notice to actually talk today. So thank you very much, Nikolay.
Thank you for inviting me. Some time ago, Shir El-Shok was invited with 2 days notice to give a talk in Amsterdam, which he interpreted as a way to decline the invitation, but I did not interpret it in this way, so I accepted, so you'll hear a talk from me. Good. So obviously I couldn't come in Paris in person, unfortunately, so I put a background to remind you that, you know, Paris exists, I guess. Good. So I'm going to talk about...
we cannot see your next slide.
Sorry?
We cannot see your next slide.
What do you mean? Do you see?
We cannot see your background.
I haven't seen, I haven't moved to the next slide.
He means his background photo. You'll notice the Eiffel Tower.
Oh, the background photo. Sorry, I thought you said background in the slides.
Okay, so off not to a good start. So the jokes are not accepted well. So let's see how it goes with the science. Good. So I'm going to talk about 2 papers that appeared already. One appeared actually this morning and one more to appear hopefully within the next few weeks. And here are the people that worked very hard on this. So Anthony and Val are postdocs in Leuven. Hongmin is junior faculty in Pohang, and Kirill is junior faculty in Sofia. Okay, so what's the motivation for all this? Well, I hope I don't have to motivate too much, but the basic idea is that we may want to go beyond the leading order supergravity approximation of string theory. And in doing this in some kind of a small coupling expansion will lead to higher derivative low energy effective actions, which we'll have to deal with somehow. Specifically, what I'm interested in is all of this in the context of ADS CFT. So these will be some kind of 1 over n or 1 over lambda corrections to some endpoint functions, if you wish. And finally, you may be interested in how all of this affects black hole physics in ADS, for example. And I'm going to talk about all of these things in the context of 4-dimensional supergravity and 3D CFTs. Okay, so this will be the subject of the talk. Now, before I go into the details, I want to motivate a little bit with how you might want to approach a question like this. So we all know that these corrections to supergravity should arise from some kind of quantum stringy alpha prime effects. And in principle, we should have a way to compute them by, for example, computing scattering amplitudes of strings or some loop effects. But of course, these are not easy things to do explicitly. And so as a result, I don't think we have a systematic understanding of all corrections, for example, to 11D supergravity. And this will be the example I'm going to focus on, which will be 11D supergravity. And specifically, just to keep in mind one example, we should be thinking of these ADS4 times Sasaki-Einstein backgrounds of 11D supergravity. But even if you have had these terms in 11D, anything that is not an ADS4 background, for example, if you want to compute an on-shell action or an endpoint function in ADS4, you have to deal with some annoyingly involved 11D Lagrangian, which the leading correction will be at the 8th derivative level. Okay, so this will be, if you wish, the 11D approach that you may want to take. And of course, this looks quite hard. And as far as I know, there are not many explicit results available in the context of ADS CFT. Okay, so motivated by this, we wanted to find a different approach. And so here is what we did in a couple of minutes, if you wish. We used 4D n equals to 2 supergravity and view this as some kind of a low energy, large n approximation to 11D supergravity. And then studied the possible higher derivative terms in 4D supergravity. And then the coefficients of these terms are unknown. And of course, I don't have a string theory to compute them because I'm in 4 dimensions. So what we did is we kind of fixed them using SUSY localization. So explicit answers for on-shell actions, if you wish, that are available to us by SUSY localization at large n. And so this idea actually works. And specifically, the example that we worked out in detail is this 4-dimensional n equals to 2 minimal. So minimal here means only the multiplet of the graviton, 4D n equals to 2 minimal supergravity, which should be dual to some kind of a universal large n sector of a large class of 3D n equals to 2 CFTs. And this idea can be, well, you can argue that it has to work due to the large n limit and the fact that you actually have consistent truncations to 4D supergravity. So this last thing is an argument, it's not a proof. So if you wish, the fact that it works in hindsight is also another kind of argument that all of this is a good idea. Okay, so this is my introduction and motivation. And at this point, I want to ask if there are any questions or comments or complaints.
You made some remark about the fact the only corrections are 8 derivatives, and that's the usual sort of x8 term, isn't it?
Exactly.
But
So,
couldn't there be other corrections that aren't driven by anomaly considerations?
absolutely. So indeed, as far as I know, the corrections in 11D, so one of them is the well-known C3 wedge x8 term, which is the coefficient of that is an anomaly, so it's easy to compute. There are other ones like R to the 4th terms
right,
that have been actually computed, some of them, as far as I know, by Michael Green and Pierre Van Hoff, who is probably in the audience, or maybe not, I don't know. But as far as I know, we don't know all the coefficients. So like f to the 4th, the coefficient of that is not known, as far as I'm aware.
I think f to the 4 is known, right? All what is quartic is known. It's just that the full nonlinear completion of the unique supersymmetry
Right.
means that it is not known. But
so I would like to know the nonlinear thing because I want to find actually solutions and then compute on-shell actions, for example, or black hole entropies and things like this. Okay. Any other comments or questions? Good. So I'm gonna move on and give you a flavor of how the 4D calculations work. They're not easy and they're not very illuminating or easy to explain in a few minutes. So I'm just gonna give you a flavor of how they work. Good. So the formalism that we're going to use is what's called 4D n equals to 2 conformal supergravity. And recently there has been a book published on this, and one of the authors is in the audience, Edo. So if you want to learn this, you can go and buy this book. But I'm not gonna bother you with all of the details in this book. What you need to know is that you can use this these tools to construct 4D n equals to 2 supergravity actions. And in general, if you want to study arbitrary method multiplets, you have a number of free functions in your 4D actions, which is, for example, a superpotential, a prepotential. All of these things should be somehow chosen or computed. But in our case, we will be doing minimal supergravity, which means without any matter fields. And so these functions will actually be reduced to constants. Someone has a question or? Oh, just background noise. Okay, I'm gonna move on. So for us, the multiplets we will need are these off-shell multiplets.
Please unmute yourself, Nikolay. I mute everybody because there was some background noise, and you should unmute yourself.
So I had to stop share to unmute. So I'm sorry.
Sorry for this.
Let me try again.
Guillaume, the solution is to look at the list of participants and then see who has the microphone, because when somebody is talking, and just mute them personally. If you see there are some microphones which are on and moving. If you look at the list of participants and just mute them all.
Can you hear me now? And can you see?
Yeah, perfect.
Yeah, you're good. Go ahead.
Good. So what I need are these multiplets. So what's called a Weil multiplet, which contains the metric and a bunch of other fields, a vector multiplet and a hypermultiplet. And it's important to understand that these things are off shell. So to go on shell, which here means to get to fix the conformal symmetry and a part of the gauge symmetry, you have to solve. I mean, most of these fields here are auxiliary fields, and you have to solve the equations of motion for that. So this is what people in this business call going on shell. So you go from the conformal supergravity to the usual Poincare supergravity.
Wait a minute, you've got an SU2 gauge group. That's a bit bigger than you need, isn't it?
Exactly. So a part of the process is that actually you kind of gauge fix a lot of these fields. And in the process here, you can introduce a gauging so that you can get the usual 4D n equals to 2 Poincare supergravity. So in the next slide, I'm going to show you the result of this kind of operation here. So the details are in the paper, but here's what the answer is. So there is a unique two derivative action with one constant, which is just a Newton constant. Okay. At the 4 derivative level, which will be what we're interested in, there are two independent SUSY kind of invariants. They have various funny names, the Weil square invariant, which was studied here, and then there's a T-log invariant, which is independent and was studied in this other paper. There are no D terms, and so that's all that you have. So you have two kind of independent invariants that you have to deal with at the 4 derivative level. It's important to notice that, well, we have worked all this out, is that what is an auxiliary field at the 2 derivative level can actually acquire a kinetic term and be a dynamical field at the 4 derivative level. And another comment I want to make is that for many of the things that we want to compute them in Euclidean signature, things like on-shell actions. And so a lot of the things we had to do are in this Euclidean supergravity formalism studied in this paper. Okay, so here is how the answers look like.
Sorry, Nikolay, can I ask a question here?
Yes. Yes.
Can you go back to the previous slide? What does this last comment mean? I mean, isn't the minimal supergravity multiplet enough to describe the dynamics of, so there are new states?
Yes. So you mean about this additional fields here that I mentioned? So indeed, we find a new propagating spin 2 mode and spin 1 mode. I'm going to talk about all of this later on in the talk.
Okay.
Okay.
Sorry, Nikolay?
Yes.
If I may ask as well, I mean, usually one takes those higher derivative correction as the first term in an infinite series for a non-local action. So we don't consider them dynamical, but rather we consider that they are starting from higher order corrections, such that those new degrees of freedom disappear. Don't you do that here? Or
you will see exactly how this comes about. Indeed, that's on. What I'm going to mention here is that these constants, C1 and C2, they control these two extra terms in the action that I'm including, and they're suppressed by a power of 1 over n in comparison to the leading order, two derivative term.
Okay. Usually when you have dynamics that's induced by things of fourth order and derivatives, the propagators, the poles, become pathological. Is that going to be a problem?
You will see what happens. I will try to explain that. So another way to think about this is that these extra modes are very, very massive, and so yeah, they have a mass that they're not a Kaluza-Klein mode on the internal sphere, but they come from some kind of M theory modes. Their mass goes as n to the 1/2, scales as n.
They don't have poles of the wrong sign. They're not ghosts.
I don't think so.
they would have if you were truncating the action, but you are doing an asymptotic series in 1 over n, so they don't.
Yes,
care.
exactly. So because of 1 over n, I don't think there's any issues. Anyway, let me move on. These modes will not be the most important part. I'll be mostly interested in on-shell action calculations. So here is the schematic form of the Lagrangian. So there is the usual Einstein-Maxwell piece with a cosmological constant, and then 2 extra pieces. And one way to think of these C1 and C2 is that they're encoding information both about the choice of internal manifold I make, but also about the couplings of these 8 derivative terms in 11 dimensions. So ideally, I would want to compute C1 and C2 by starting from M theory and reducing on a Sasaki-Einstein manifold, for example. But I don't know how to do that in full detail, and so I'm kind of parameterizing my ignorance with these C1 and C2 constants.
Sorry, Nikolay. So in this action, there is only the metric, right?
No, Maxwell field also.
Maxwell field. Okay.
So here's the explicit action at the 2 derivative level. It's just Einstein, Maxwell, and a cosmological constant. So the parameter in at the 2 derivative level, the dimensionless parameter is L squared over G Newton. Okay, so I have one constant, if you wish, to fix microscopically, and at the higher order level, I have these 2 other Lagrangians I have to add. And again, you'll see here the Weyl tensor built out of the metric, of course. And here is a Maxwell field. And this is the self-dual part of the Maxwell field. And this is the anti-self-dual part. And there's an RFF coupling and so on. Okay? And this last piece is just the usual Gauss-Bonnet term. Okay? So this is with the bosonic Lagrangian I'm going to be working with. And what supersymmetry buys you is that instead of having independent coefficients for each of these terms in the action, I have only 2 independent constants, which are C1 and C2. So if you wish, Suzy bought us a word identity that relates the coefficient of the Weyl square with this RFF, for example. Okay, is this clear?
Nikolay, is there some F wedge F term also?
Very good, very good. Yes, in principle, there is an F wedge F term. For the moment and for this talk, I will ignore it by imposing invariance under parity. So these actions here are invariant under parity. If you break that, there will be F wedge F and also R wedge R. So there will be actually another independent constant here that will come from R wedge R.
But
R is the Riemann tensor.
But the ones coming from string theory, you always get this term, right? I mean,
Not always. Not always. I'm going to talk about this. So for M2s, for M2 branes, you do not get F wedge F unless you add a matter coupling. So if you have scalar fields in the problem, yes. But if you do not have, if it's only minimal supergravity, you do not get F wedge F.
Okay.
Okay. Okay. So now I have an action and I want to solve equations of motion, for example. And the nice thing that happens is that the solutions of Einstein-Maxwell theory, the solutions that come from this action here, from this simple action, actually solve the equations of motion for the full action. This is a non-trivial fact, and similar things have been observed in different contexts. I don't have a good explanation for this, but it is a fact of life. Okay, so the solution space.
Quick comment, Nikolay. The Gauss-Bonnet term is a total derivative.
Sure. Yes.
Is there a similar? So therefore, it doesn't change the action a priori, except in the quantum theory. Is there a similar statement about this other term, this file term?
No, I don't know of any statement. For example, if I change this 1/2 to 11/2, what I mentioned will not work. So I'm not sure what is so special about this extra term that allows me to keep the same solution as the equation of motion of this term. If anyone has an argument, I'll be happy to hear.
Okay, obvious question is it a total derivative? Because the Gauss-Bonnet term is a total derivative.
Yes.
And if you change the coefficients, it's not a total derivative.
It is not a total derivative, and this is what I want to mention here, is that actually the full equations of motion are affected. So I have something that I will call a four-derivative solution in principle, new solutions that we haven't studied in detail, but the point is that anything in the yellow region is also a solution of the bigger theory.
But Nikolay, sorry, if you take just Weil square, you know that you can rewrite it as a total derivative plus term, which are Ricci's tensor, etc. So you know that using the equation of motion, you remove them. Isn't it the same that is appearing in the supersymmetric case here?
It is not the same. So I want to claim that because of these other things which I have here, like Ricci tensor with the Maxwell field and these other couplings, this is not a total derivative. And again, it's manifestly true when you write down equations of motion, you see that you will have a modification of the equations of motion.
But presumably the Gauss-Bonnet terms don't modify the equations of motion, right?
Correct.
Good. I'm happy.
Yeah. So,
sorry, Nikolay, related question. So any solution or only the BPS solutions? Any. Okay.
Any solution, and then the other non-trivial fact is that actually the Suzin variations also are kind of nice. So the BPS solutions at the two derivative level remain BPS. So in principle, you could ask, are there more general BPS solutions? Are there more general non-BPS? Presumably you should have them. We have not studied this in any detail. So for the rest of the talk, I'm going to study only this yellow circle and in some specific examples also the BPS. Any questions about this?
Would you not have? I mean, it's you draw it as if the four derivative solutions are a huge big space, but should they not come as small corrections on top of the two derivative solutions?
Right.
And similarly for BPS.
Right. So this is obviously schematic. So indeed, you should expect that anything that is not a two derivative solution will be a small modification of the two derivative solution. Okay. So indeed, the picture may not be very illustrative of what actually happens.
It's topologically correct.
Yes. Okay, good. That's all I wanted to say about 4D supergravity. So if you don't know supergravity and supersymmetry, well, you should learn, but also you just need to know the information on this slide here. Okay, good. So let's go and do holography with all of this. So an important observable in ADS CFT is the on-shell action. And the on-shell action without insertion of any sources of the supergraph theory should be dual to the path integral, the free energy, the partition function of the dual QFT. To compute this, you have to perform something that goes by the name of holographic renormalization, which is just a device that allows you to cancel the UV divergences arising from the asymptotically ADS region. And all of this is well known. The slightly kind of the slight addition that we had to deal with here is that I actually have these extra terms in action, and I have to learn how to apply the usual tools to this new action. This isn't possible to do, and it's actually simplified by the following two facts. The first thing is what I said, is that I'm going to study only the two derivative solutions. And another thing that happens, and this is an on-shell statement, is that on the two derivative solutions, this identity is true. So the three on-shell actions that I had above, on-shell, are related in a specific way. So using these two facts and using these counter terms, so I have to add a counter term for the usual two derivative action, which is here. This thing is well known. And then there's another counter term which was written down actually in '88 by Rob Myers, which is given here, and they're built out of the metric and the induced metric on the boundary, and then the curvature of the metric on the boundary. So using all of this, you arrive at this beautiful equation in the box. So how should you read this equation? What you have here is the complete finite answer for the on-shell action of this four derivative theory, evaluated on any solution of the two derivative equations of motion. This curly F is the usual on-shell action of the two derivative solution. So this F has been computed in many, many papers for various backgrounds. And chi is something that I want to call the regularized Euler number of the four manifold. So I have a four manifold, but it also has a boundary, and so I have to compute this kind of a Gauss-Bonnet term plus a piece that cancels the divergence at infinity. So these two things, curly F and curly chi, depend on the solution that you choose, and the rest are some constants that are fixed in the Lagrangian of the theory. Okay, so this is, if you wish, the main on-shell action result. And just to show you that we can actually compute stuff, I have made a table here that is these quantities, curly F and curly chi, for a bunch of BPS backgrounds. So I have chosen BPS because I'm going to use these things later on when I connect to SUSY localization, but in principle I can do this also for non-BPS backgrounds. Okay? And just to give you orientation, so the first line is just empty ADS, rather Euclidean ADS with an S3 boundary, so H4 if you wish, hyperbolic space in 4 dimensions. This line here, in the QFT community, this thing can be called a squashed sphere, so it's some kind of a solution that asymptotes not to the round S3, but to a squashing of the S3, parameterized by this B. This is the Kerr-Newman black hole. This thing here is the Reissner-Nordstrom Euclidean black hole with a horizon of genus G. Okay, so just a bunch of examples. Okay, I want to give you now explicit details on 2 of these examples. The first one is this squashed sphere. It looks a little bit messy. So this is the metric in some special u1 times u1 invariant coordinates, phi and psi. And if you wish, a certain combination of x and y give you the radial of ADS. Those of you who have seen a black ring in their lives should recognize a little bit this coordinate system. But for us, what's important is this f and chi. So here they are, and they're very, very simple. Another solution is, as I said, this Euclidean Weierstrass-Nordstrom. It was actually written by Larry Romans in '91 in a Lorentzian signature. So here we have Euclideanized this. It has an electric charge Q. The magnetic charge is actually fixed in terms of the curvature of the Riemann surface because I have imposed a certain amount of supersymmetry. So if I didn't have SUSY, this parameter here will be arbitrary, but now I have to relate it to the curvature kappa of the Riemann surface. And so again, I can compute explicitly this curly f and curly and chi for this background. Okay, keep all of this in mind. Now, another thing that I can do is I can compute the two-point function of the energy momentum tensor of the dual CFT by doing a very standard Witten diagram, which is just a propagator of the graviton in ADS4. This will be affected by the presence of this extra term in my action. And so the two-point function coefficient of the energy momentum tensor has been computed for arbitrary theories with a 4 derivative action without any amount of supersymmetry. And we just use this for our case to extract this answer. Okay? So as you see, there's a leading order term, L squared over G Newton, and then a correction due to this Weil squared term in the action. We can do here a consistency check of what I told you on the previous slide and this answer, because there is a non-trivial word identity that relates a derivative of the squash sphere. So I told you about a squash sphere here. If I would differentiate this free energy or on-shell action with respect to this B and put B to 1, I get exactly this CT coefficient. And we did this calculation explicitly and got exactly the same answer. So if you wish, we compute it in two ways, the same thing. It's exactly the same. So we have a consistency check of the calculation. So we have not messed up here yet. Good. So here is this issue with the spectrum. So what we did is we studied the fluctuations around anti-ADS. So I have an action, I can linearize all fields in this action, bosons and fermions. We did it with the fermions also, and study the masses of all fields. And then from the masses, I can map this to dimensions of operators in the dual CFT. So here's how the spectrum looks like. So there's a massless spin 2 multiplet, no surprise. This is dual to the energy momentum tensor in the dual CFT. And here I have organized it in a 3D CFT notation. So there is a conformal primary, which is a spin 2 operator of R charge 0 and a dimension 2. This is the U1 R current, if you wish. On the boundary, in the bulk, it's just a Maxwell field, the photon, if you wish. Then there is a supercurrent, and then there's an energy momentum tensor here. But the other thing that happens is that all these auxiliary fields, well, not all of them, many of them, as well as the metric itself and the spin 1 field itself, they also have massive modes now because of the extra terms in the action. And you can compute all of the masses of these modes. So as you see here, I have a scalar, a spin 1/2, spin 1, many spin 1 modes, actually spin 3/2 modes, and a massive spin 2 mode. And this organized into what's called a long multiplet of n equals to 2 superconformal symmetry that looks like this. So these are all of the fields in the multiplet. the thing in red here is the superconformal primary. So it's again a spin 1 primary. And this, all of the dimensions in the multiplet are controlled by a quantity that we call little delta that we can compute explicitly, and it's given here. So as you see, little delta, first of all, this thing should be a real number if you want a unitary CFT, so I get a lower bound on this. But more importantly, L square over G Newton is much, much bigger than C1 minus C2, simply because if you wish, this is the leading order term, and this is the subleading order term in my derivative expansion. If you want some kind of estimate for the scaling, if you have M2 branes in M theory, this is going to scale as M to the 1/2. So these are not the usual Klotz-Klein modes. So this is some kind of an M theory mode that is unprotected mode, lives in a long multiplet of the CFT. I don't know of any other way to
sorry, Nikolay, can I ask a question? Could you in principle have 6 derivative corrections and so on?
Absolutely.
So then, I mean, I presume that at the scale at which these modes become important, also those corrections would become important. So it's not that you can necessarily conclude that you've truncated your action. Your action has a cutoff, which I'm not sure is above the mass of this mode. So okay. I'm not sure whether I should take them seriously.
Let me emphasize one thing. I don't think it's a good idea to talk about a cutoff here, because this is a consistent truncation, not a Wilsonian effective action. I have ignored infinitely many modes with masses that are much smaller than this mass. All of the Kaluza-Klein modes that are dimension order 1 operator, or n to the 0 scaling, I have ignored them in this business. And this is due not to a Wilsonian argument, but to the special thing that happens in ADS, that we have consistent truncations. So if you wish, the existence of this universal mode is some kind of a 4-derivative signal that you have something like a consistent truncation with massive modes.
So it's a consistent truncation of what?
Of 11D supergravity with
how many derivatives?
8 derivative terms.
8 derivatives.
Yes.
But why would you take seriously the truncation to this just 4 derivative term? I agree with Monica somehow. I mean, those mass are higher than, I mean, usually you don't consider them and there is no ghost problem whatsoever, whereas here there would be ghosts if you were taking them seriously.
Okay. I don't have a proof that what I'm writing down at the 4 derivative level is a consistent truncation. If you wish, I'm assuming that, and I'm seeing what is the outcome of this. So as you will see, things are going to start working very well, and so now we have to understand. If you don't believe the story, you'll have to explain why it works so well.
Just to understand, these numbers that you're getting here are around ADS?
Yes, around ADS4. So if you do not like the story about the spectrum, you can just ignore it for the rest of the talk. So I will focus on shell actions now. And so if you wish, I'm not going to study a propagating mode, so hopefully that's better.
And anyway, they have the wrong sign for the kinetic term, most of them, right?
No. These guys are perfectly fine. There are no ghosts here.
So holographically, would you be able to compute 2-point functions and, for example, 3-point functions of 2 of these 2 stress tensor operators and
exactly
this new guy?
If you believe that what I'm giving you here is a consistent truncation, then yes. If you don't, then no. I mean, now I've computed a 2-point function, but in principle, I can study this horrible linearized action and do Witten diagrams and compute a 3-point function. We have not done this because it's a pain, but you could eventually do it, yes.
I'm sorry, let me ask also a sort of simple question. Consistent truncation, as far as I know, is essentially a property, whereas if you set in the equations of motion a set of fields to 0, this would give you a solution of the whole theory. Now, if this is a property that one is using to define consistent truncation, does that mean that the fluctuation spectra of the two theories are the same?
It means that the fluctuations of the fields that you keep in your truncated actions will not be affected by the extra fields.
So they will not mix.
Right. This is why, for example, this is why the energy momentum multiplet is universal for all these CFTs arising from a Sasaki-Einstein manifold. I'm ignoring all of the Kaluza-Klein modes about these details of the internal manifold, and still the spectrum stays the same. So if you wish, this big multiplet should be viewed, at least in my head, as a massive partner of the energy momentum multiplet.
Okay, thank you.
Sorry, Nikolay, I was cut a bit. So what you mean by consistent truncation is that you have some higher order equations of motion, and then you plug in solutions to the lower order equations of motion and show that.
Well, ADS4 is a solution. If you wish, ADS4 S7 is a solution to all orders in an 11D, right?
Mm-hmm.
So I'm not using some other solution. I'm using the thing that we know and love has 32 supercharges and is, completely fine to all orders, but I'm expanding not the 2-derivative action, I'm expanding the 4-derivative action. And that's what gives me this extra piece. I guess we can talk about this afterwards. As I said, it won't be essential in the rest of the talk.
Yeah, I guess you should go ahead.
Okay, let's talk about black holes a little bit because I'm running out of time. So I have a higher derivative action. It has black hole solutions. For example, think about static ADS Kerr-Newman, not static, stationary ADS Kerr-Newman black hole. And you can start computing its world entropy, for example. So this is the famous formula. What you have to do is you have to differentiate the Lagrangian with respect to the Riemann tensor and integrate it over the horizon, contracting with some special bivectors. And here is what happens. This is a final answer for any black hole in our action. So the Bekenstein-Hawking entropy will be corrected by this alpha, which is again C1 minus C2, if you wish. And then there is an extra term due to the fact that you have a Gauss-Bonnet term in your action, and this is a purely, if you wish, a topological term. So chi of H is the Euler number of the horizon of the black hole. Okay, so that's a simple answer for what's the world entropy. And again, it's independent of supersymmetry. So it's independent of the supersymmetry of the solution. It relies on the fact that I have a supersymmetric action, of course. Okay, if you want to study additional things, then I mean, not only the entropy, but other things about the black hole, like the conserved charges, you have to work a bit more, but it's kind of algorithmic. What you have to do is you have to compute some kind of a Komar-like integral, and we did that. And what happens is that the magnetic charges are not affected by these extra terms in the action, but the electric charges are, and they're affected again by this alpha. So there is a simple modification of the electric charge of the black hole due to the extra terms in the action.
Does the ADM mass get modified? Oh, sorry, thank you.
Yep, there it is. So the same happens with the mass and the angular momentum. The calculation is a bit more messy, and that's why I'm giving you only the answers, but it works in the same way. You have to do a Komar integral, basically.
So So that means that the black hole area is, there's a 1 plus alpha in front of your entropy term. If you go back to the previous slide.
You're getting ahead of, I'm going to comment exactly on this now. So the first thing, once you know all of this, you may want to try and do a consistency check of everything I've told you. So in like a few slides ago, I told you what the on-shell action is. So that's I. Now I've told you what's the mass, the entropy, the charge, and the angular momentum. And you may want to check whether this thing that's called the quantum statistical relation in black hole physics is obeyed. And indeed, it is obeyed. So essentially, these quantities here, t, phi, and omega, are things that are not changed because they only depend on the two derivative solution. So they're, if you wish, intensive quantities. And these other things, the mass, the entropy, the charge, the angular momentum, are modified in a very specific way because they're extensive quantities. And so this indeed works, provided that the Euler number, this thing in the on-shell action of the 4 manifold, is the same as the Euler number of the horizon. I'm not sure how to prove this completely generally mathematically, but on examples, it always works. So this thing always works, which is another consistency check of the story. And I want to make a comment exactly, I think, about what Nick had in mind. So the extremality ratio, Q over M, so this is usually what people call the BPS ratio or the extremality ratio. So Q and M are individually modified, but as I told you, Q and M are modified in the same way here, so the ratio is not modified. However, the entropy here is modified in 2 ways. So both by this 1 plus alpha, but also by this extra piece here. So the conclusion is that the extremality ratio is not related to the change in entropy, at least in this model. And I'm making this comment because there has been some interest in the literature with relation to the weak gravity conjecture and so on. So anyway, this is a specific model that you can actually compute all of this in gory detail and see what comes out. Good. I'm going to stop here with the black hole story and move to the CFT. How much time do I have? I don't hear you.
Sorry, you have almost 15 minutes, I would say.
Okay, great. So I'll try to convey the main idea of what we did here. Okay, so now everything I told you here so far, even though I have appealed to intuition about 11D and so on, is strictly speaking 4D supergravity. There's been no string theory, no M theory, nothing like this. Now I want to make a connection to 11D, but not by uplifting, but by comparing to a dual CFT. So I will assume that ADS CFT is true, which I hope we should agree by now that that's a good idea to assume. And I'm going to study a specific instance of 3D CFT. So M2 branes arising at the tip of a Calabi-Yau cone over a Sasaki-Einstein manifold in M theory. So just by scaling, Lagrangian scaling of the observables in the CFT, you can argue that this L square over G Newton is going to scale to leading order at large n as n to the 3/2. And I'm going to allow, so this is L square over G Newton in 4 dimensions. So I'm going to parameterize my ignorance how this scales at subleading order by the constant A. So I'm going to put here a constant that parameterizes this n to the 1/2 scale. In addition, the constants C1 and C2 are subleading, so they have to scale as n to the 1/2. Okay? So these constants in red, A, capital A, little a, and V1 and V2 are not going to scale in n, with n. So they will be order 1. Okay, so I'm going to put this information into the on-shell action that I've computed, and I find this answer. So I find that my on-shell action, or if you wish, the free energy of this class of CFTs should look like this, where again, chi and f, you can think of them as geometric quantities that parameterize what manifold I put my 3D CFT on. So they will be different if you put the ABGM model on a sphere or a squash sphere or S1 times S2 and so on. So now I still don't know what the constants are. And the whole idea here is to fix them using information about the path integral of the ABGM theory. So what we did is we used the S3, so the round sphere path integral, which can be computed to all orders in n by using a beautiful paper by Marinho and Putrov. And then CT can also be computed up to subleading order in n, so this two-point function of the energy momentum tensor. And so using this information from the QFT literature, I can fix all of the constants. Here's how it works. So we did this for two models. So the usual ABGM model at level K is here. So this arises from N2 brains probing a ZK singularity. And then there's another class of models that is just the usual Yang-Mills with n equals 4 supersymmetry, 2 plus 1 dimensional Yang-Mills, coupled to one adjoint and NF fundamentals. This can also be realized in M theory by another kind of ZNF orbifold of the seventh sphere. So these are, if you wish, closely related but independent models. So for both of them, the free energy at large n is known, and also CT at large n is known, to leading and subleading order. And that's all we need to fix the constants. And so here is what the constants are. So the capital A is giving you the leading order in the n to the 3/2 piece. The coefficient of n to the 3/2 is here. And these other two constants give you the coefficients of n to the 1/2. I have two, if you wish, independent n to the 1/2 contributions, and here are the coefficients. Okay? Good. There's also a consistency check that can be done for these two models. Some information is available also for the squashed sphere for very specific value of the squashing, because this model with a very specific squashing is related to what's called a topological vertex of Aganagic and Vafa and friends. And Hatsuda has computed the matrix model to subleading order in n for this value of the squashing. But essentially, what you see here on the slide is everything that is known to subleading order in the dual QFT. But here I told you that I know the full answer from the Sugra story. So now I can start making, if you wish, Sugra predictions for the dual QFT. And here's how they look like. So here is what we claim the leading and subleading answer for the free energy on a squashed S3 of ABGM will look like for arbitrary B, arbitrary squashing B. Okay? And you can keep on doing the same thing. So this is what's called a topologically twisted index. This is some kind of a Witten index that computes, if you wish, the entropy of this Reisner-Nordstrom black hole. So if you wish, we computed the subleading entropy of the black hole microscopically. Then the superconformal index, or the S1 times S2 path integral. This omega is, if you wish, a fugacity for the rotation on the S2. It's a free, it's a refinement of this index that you can introduce compatible with supersymmetry. And so that should be the full answer up to order n to the 1/2. And some of these, so for example, this answer you can compute independently for some special value of the genus, and it agrees with what's available in the literature. So these things are specific things, specific answers for supersymmetric observables, but I just want to emphasize that I can now do all of this for a non-SUSY black hole also, if I wanted to. Good. So very quickly, what is the paper that we put out actually today about? We can do all of this for another class of models in M theory arising from M5 brains. If you don't know what these models are, you're not going to learn it here. But the basic idea is that you put the 2,0 theory, the 6D 2,0 models on a hyperbolic manifold M3. you do a topological twist, you put the size of the manifold to 0 because you've just done a topological twist. The low energy theory should be independent of the size, and you get a 3D n equals to 2 CFT or QFT on R3, and this thing is called class R QFTs. And beautifully, DGG here, they claim, a la AGT, that there's a 3D correspondence, if you wish, between observables of this 3D QFT and Chern-Simons theory on the hyperbolic manifold. So essentially, computing the partition function of these 3D n equals to 2 QFTs on various manifolds can be mapped to computing Chern-Simons invariance on a hyperbolic manifold. So that's the claim to fame, well, one of the claims to fame of DGG. Okay, so our idea here is very, very simple. Is just to do all of this in the Lagrangian limit. And Dongming Gang and his friends have been doing this for a number of years, and we have applied their results in our context. And here is what we find. So this is the answer for the free energy of these class R theories for any choice of supersymmetric background B, so a squared sphere, S1 times the Riemann surface, the superconformal index, a length space, anything that you choose here, this thing holds. The volume, this volume factor is the volume of the hyperbolic manifold, which is a topological invariant, even though it's a volume. That's a deep fact of hyperbolic manifolds in 3D. And then this DG and HG encode information about the 2,0 theory. So the 2,0 CFTs in 6 dimensions come in families associated with a simply placed algebra, and these are just the dimension, the Coxeter number, and the rank of the algebra, or the group. Okay, so we have a compact formula that captures the leading n cubed, but also the subleading n to the power 1 contributions to all of these observables. For those of you who know anything about anomalies and the 2,0 theory, you should look at this and say, aha, I have seen this. This looks a lot like the anomaly polynomial of the 2,0 theory. And indeed it does, but I don't have a very good idea why. So it would be nice to understand why this thing looks so closely related to anomalies of the 2,0 theory. Good. So that's all I had to say, basically. So just to give you an overview, I told you how to study
yeah, you still have some time, right? So you should not rush up if I see you already at the summary.
Right. So, well, at this point, if anyone knows why, if anyone can answer this, I'll be very happy to hear. My only idea is that this is some kind of a path integral that should be computed in 6 dimensions. So I have to integrate somehow over some background in 6D. And in 6D, the partition function is not a function. It's because I have anomalies, so I'll have some abstraction to this. And so this, if you wish, is some kind of should come out of equivariant integration of the 6D anomaly polynomial. That's my only idea, but I don't know how it's going to work in detail. Anyway, and I should emphasize that I've written here E67 and E8. These are not the Lagrangian models, but the formula is so beautiful that somehow it has to be true also for E67 and E8. I don't know how, but for AN and DN, these are obviously admit a Lagrangian scaling, and this should be true. Okay, but yeah, that's all I have to say here. And by the way, this F and chi are the same F and chi that I had on one of the previous slides. So we can have a table of them, and all of these things are exactly the same F and chi. Good. Anyway, so what I've told you about is how to study 4 derivative actions in 4D n equals to 2 minimal supergravity with a U1 gauging. And then I told you how to study the consequences of this modified actions for holography in computing on-shell actions, computing the two-point function of the energy momentum tensor, and then this clearly confusing and controversial thing that I said about the mass is spin to multiplet. If you're still confused or if you're unhappy, just ignore this. Then I told you how to study the effects of all this on black hole physics, specifically entropy and all kinds of thermodynamics. Also, I've talked about how to use all of this in the context of specific ADS CFT models, so AVGM-like theories and also M5 brains, and how to use it to compute new observables that, as far as I know, have not been computed yet by SUSY localization. Good. So what's the homework assignment? Well, there's many homeworks. Some of them we're working on, others I have no idea how to approach at the moment. So obviously you should extend all of this to matter coupled Fourier supergravity. We have a pretty good idea how to do this for the STU model at the moment, which again arises from M theory as a consistent truncation. You should be asking, can I do this in 5 dimensions, in 6 dimensions, in 7 dimensions? You should be able to. And some results in the context have been already obtained by these people here. We're also looking at this, especially in 5 dimensions and 6 dimensions. You can ask, okay, so far I have imposed n equals to 2 supersymmetry in 4 dimensions, and I have told you that there are 2 independent constants. You could expect that if you impose n equals 4 supersymmetry instead of n equals to 2, you should find a relation, a word identity between these 2 constants. We think that this should happen, but we have not understood it in full detail yet. These 2 things here are just emphasizing that some of the things we computed, as I told you, are new results on the QFT side. It will be very nice to independently confirm them by revisiting these matrix models arising from SUSY localization and computing not only the leading n to the 3/2 term, but also the subleading n to the 1/2 term. I've told you how all of this works for n equals to 2 models in 3 dimensions that arise from M2 and M5 brains. There's other well-known large N CFTs that arise in string theory. They come from D2 brains or wrapped D4, D8 brains. They have interesting scalings with N of the free energy. So these are the leading terms. It will be interesting to study the subleading ones using our tools. Recently, there's been this beautiful work of using SUSY localization results of the type I told you about to, if you wish, constrain or compute the string theory or M theory corrections to supergravity. So kind of the same idea, but directly applied to the 11D effective action or the type 2B effective action. And it will be nice to relate what we did in 4 dimensions to what was done upstairs. And of course, as was already asked, I've studied a 4 derivative term, but there should be a 6 derivative, an 8 derivative, and so on. This will come with subleading powers at large N. If you do one loop calculations in the bulk, you should find also the log N pieces. And so all of this, of course, will be interesting to study. That's all I had to say. Thank you very much. Thanks.
Thank you, Nikolay. We can unlock if you please unmute if you want to upload the Costa.
Yeah.
Are there any questions?
Yeah, maybe can I ask a question, Nikolay?
Sure, Francisco.
So in some of the examples you showed, you have other massless fields, right? So in particular, the n equals 6 and n equals 4 cases. Now, one might expect that when you compute the free energy at subleading order, you have one loop corrections from these massless fields. Why should this be captured by a local 4 derivative action?
Excellent. So let me remind you that I had in the title the word unreasonable. So indeed, some of the things I'm doing, if you do not have optimism, you should not be doing them. But I think we should be doing them. Specifically about the loop effects, I want to argue that the fields that you called massless, they're not actually massless. They have masses, right? But they have the same. So, like for example, this STU model in 4D is a very good example. So this STU model adds a vector multiplets, which, if you wish, in them have scalars that are dual to specific mass deformations of ABGM. So dimension 1 and 2 operators in ABGM.
Right.
But those things should not affect the log n term, I think.
Mm-hmm.
I'm not sure. So if you wish, you could be asking already this at the level of the two derivative action. How can I ignore these modes and study only the dynamics of the energy momentum tensor? So this is this Lagrangian magic of the consistent truncation.
That's okay. This is okay. I mean, here we are discussing one loop corrections to the free energy, right? So this is the subleading.
Yes, but I think one loop comes at sub-subleading. So I'm talking about, so this answer here, this answer, for example, for the free energy, has an n to the 3/2 piece, as the n to the 1/2 piece, and has a log n piece. So the log n is the one loop effect. So, for example, the coefficient of the log n has been computed around ADS 4S7 by studying this is a paper of Afashok Sen and Marino and other people I'm forgetting. So the coefficient of log n can actually be computed by studying loops in 11D supergravity. Loops of the KK modes, if you wish, of the massless fields in 11 dimensions. And Ashok Sen has an argument that these higher massive modes will not affect the coefficient of the log p's. So if you wish, n to the 3/2 is the on-shell action of 11D supergravity. The log n is the one loop modes in 11D, and the n to the 1/2 is somehow on-shell action of the 8 derivative terms.
Mm-hmm.
I'm not sure if I'm explaining well, but that's I think how the scaling works.
Francesco?
Yes, hi Nikolay. So I have a question about the slide that you just had on. What is the status of the ABJM with the say massless flavors? How does that fit in this story that you told? So did anybody compute it, for example, the subleading term due to flavors with localization, or?
So if I'm understanding the question correctly, you're asking about precisely these things, these what I would call in the bulk of vector multiplet. So adding operator multiplets that contain as the lowest component a scalar operator and as the highest a flavor current.
Yep.
Right. So those things are precisely the thing we're studying now in what I would call the STU model. So we have added precisely these U1 cubed flavors, and we know what the answer should be. From the SUSY localization, it has been done in a very nice paper by Nosaka. It has been computed, but for very specific values of the real masses. So it has not been computed fully generated. So if you wish, in this full answer, every term here will have a function depending on these real masses, which are associated with the flavor symmetries. And we have a conjecture what these functions are from our supergravity analysis. And in the QFT, it has been computed only for specific masses. That's as far as I know.
Okay, thanks.
Is there other questions? if not, I may come back on those other modes, massive mode of the four derivative actions that I did not like so much. But I'm not sure I got your interpretation. You want to interpret them in ADS CFT by saying there are actual mode on the dual CFT that would correspond to them. Is that what you are claiming?
Yes. So I don't have a proof, but I would like to conjecture that just like the energy momentum tensor is associated to every 3D CFT, so this is, if you wish, the controversial thing I'm trying to claim here. Every 3D n equals to 2 CFT, holographic or not, should have a multiplet like this one, right? We all agree on that.
Sure, yeah.
Now I'm claiming that holographic large N CFTs, for example, arising from N2 branes or N5 branes, should also have a multiplet like this, always. So these two are universal multiplets, always present, I want to claim.
Okay.
So this is, if you wish, what I called at the beginning of the talk, I called large N universality.
And the fact that the sign become correct is an ADS thing due to the cosmological constant, because of course in Minkowski, in flat space, it's not, right? So,
exactly, yes, yes.
Okay, thanks. Is there any other questions? Well,
yes. Let me continue on this, right? Is the sign always going to be, do you predict the sign of these modes to always be correct, and so that there are never any ghosts from higher derivatives, supersymmetric higher derivative corrections?
Right. So if you wish, if you are really optimistic, which of course I want to be, you should consider what I'm writing here as a higher derivative version of the Hoffmann-Maldacena bounds, but for four-dimensional CFTs. So if you wish, I'm constraining. So Hoffmann-Maldacena bounds for 4D CFTs imply a bound on the Gauss-Bonnet coupling in 5 dimensions. Okay? So if you wish, what I'm saying here is that there should be some kind of unitarity bound in 4D n equals to 2 subgraph theories, so their coefficients C1 and C2 are not completely arbitrary. So SUSY leaves you two numbers, and if you wish, imposing that you don't have a superluminal propagation in the bulk or unitarity in the CFT gives you a lower bound. That's how I would like to interpret this. Did I answer?
Yes. Yeah.
Okay, is there any other questions? If not, let's thank Nikolay again.
Thank you. Thanks.